Any questions, comments? How are we doing time-wise? All right, I think we're just a little bit over, right? Or actually, we're early, aren't we? Okay, well, I think in that case, let's move on. So right now, I'm going to invite Dan McAvoy to come forward. We made the decision to have our technical working group be help us with this workshop, because again, it is a community thing. So we've asked individual working group members to moderate different sessions. And so Dan's going to be moderating this next one. And I'm going to give you a little introduction to Dan. He is a regional climatologist at the Desert Research Institute and Western Regional Climate Center in Reno, Nevada, where he focuses on drought and climate research and data application in the Western United States. So welcome, Dan.
Well, thank you, Marina. Really excited to be here at this workshop. It's been great working on the committee organizing this, and exciting to see all the progress in flash drought over the years, especially since the 2020 report. So we're going to kick things off today with the state of the science of flash drought. We got a great lineup of talks here. I think the way this is going to work is we'll go through each talk, and then if there's time, we'll do some Q&A after each individual talk. And then after that, there's about a 40-minute session for discussion and more Q&A if we don't get to all those questions. So let's get right to it. Our first speaker today is Jason Otkin. He'll be talking about framing flash drought and monitoring. And Jason is a research scientist at the University of Wisconsin-Madison and an expert in flash drought. So take it away, Jason.
All right, good morning, everybody. Thank you for the introduction. In this talk, I'm going to discuss a framework for flash drought identification, and then I'll spend some time discussing the strengths and benefits of different data sets that can be used to monitor flash droughts. Okay, so as we all know, a drought is a naturally recurrent feature of the climate system that refers to a water deficit occurring over some period of time. Because these deficits can impact the environment in different ways, several different types of drought have been recognized by the drought community. Traditionally, these have included meteorological, agricultural, hydrological, and socioeconomic drought. But in the past decade or so, several new types of drought have also been recognized by the drought community. These have included ecological drought, which refers to the impacts of sustained water deficits on the health and functioning of natural ecosystems. Snow drought, which refers to below normal snowpack or snow water equivalent. And then on flash drought, which are drought events that develop very quickly over a few weeks to a couple months. So because flash droughts are a relatively new concept, many people have asked me, what are flash droughts and why are they important? So the simple answer is that flash droughts represent a subset of all drought events that are characterized by a period of rapid intensification. And as we've seen many times across the United States and also elsewhere around the world during the past decade, droughts can develop very quickly whenever extreme weather anomalies persist for an extended period of time over a given location. So flash droughts tend to occur most often during the growing season, and because of this, they can have a very large impact on vegetation. This can take the form of a rapid browning of the vegetation and also potential death of those plants. This scenario is illustrated in the panels on the left, where the top two panels show how the native grassland vegetation across north central Oklahoma had rapidly browned and had most likely gone into dormancy over a 6-week period during the 2012 flash drought event. And on that stands a sharp contrast to the continued greenness of the vegetation over the same 6-week period during a wetter year in 2014. So among their various impacts, flash droughts can lead to much lower crop yields, less forage for livestock, and also to larger and more intense wildfires. Okay, so because flash droughts can have a very large impact on both the natural environment and also agriculture, it's very important that we develop robust flash drought early warning systems. So in a recent essay that we published in BAMS last fall, we discussed 5 interrelated topics that together constitute the pillars of a robust flash drought early warning system. So these include development of a physically based identification framework, comprehensive flash drought monitoring capabilities, and improved prediction of flash drought over various timescales. These three pillars in turn then lead to the ability to make more accurate and more comprehensive assessments of the impacts of flash drought, and then allows us to provide better guidance for decision making and policy activities. So in this talk, I'm going to discuss the first two of these pillars, and then the talks coming after me are going to discuss each of the next three pillars within this early warning system. But I want to mention here that to be able to successfully develop a early warning system, it requires the sustained engagement between various groups of people. So this includes, everybody from physical scientists and social scientists to the operational centers, practitioners, and policymakers. It really takes having all the people come together and having a frank and honest conversation about what it takes to mitigate drought impacts in order to, develop a good early warning system. Okay, so the first pillar then is the identification framework. It's very important to have an identification framework that you can use to both define and to identify flash droughts. So in an earlier essay in BAMS back in 2018, we argued that any definition for flash drought should account both for the rapid rate of intensification and also for the actual occurrence of moisture limitation leading to drought impacts. Now, in our essay from last year, we argue that this rapid intensification can occur either at drought onset or during an existing drought. And we argue that both of these cases should be considered flash droughts because a period of rapid intensification led to new or worsening drought impacts. So I'm illustrating both of these scenarios in panels A and B, where A shows flash drought occurring from an initially drought-free state, and then panel B shows it occurring during an ongoing drought. And you'll see that in both situations, that period of rapid intensification is very different than what you see in panel C, which is signifying a conventional drought, where you just slowly fall into drought conditions. So flash droughts are more likely to develop whenever multiple weather extremes occur at the same time. So this can include some combination of below normal rainfall, hotter than normal temperatures, low humidity, strong winds, and sunny skies. And the more of those you can get to work in tandem at the same time, the more likely a flash drought will occur, and the more likely it will be intense. So flash droughts are usually identified based on rapid changes in variables that are sensitive to land surface conditions. So things like evaporative demand, soil moisture, evapotranspiration, and vegetation health. So ideally, flash drought monitors should account for all of these environmental variables, and they should do that from before the flash drought occurs until its demise or until it transitions into a longer term drought event. So because of their multivariate nature, it's really important to use multiple lines of evidence in order to generate a measure of consensus about about whether or not flash droughts are occurring and how intense they are. So basically adopting a similar framework to what they use with the U.S. Drought Monitor. So trying to bring together multiple lines of evidence when looking at flash drought. I will mention here that with some existing operational drought monitoring tools, it's still important to keep in mind that they may not be sufficiently responsive to flash drought because they may have been designed for slower developing droughts. So for example, it may not be helpful to look at like a 6-month SPI, for example. You want to look at shorter term variables. Okay, so in the rest of this talk, then I'm going to discuss various data sets that can be used to monitor flash drought. So these are, these can basically be categorized into or placed into 3 different categories. The first of these is meteorological drivers. So these are things like below normal precipitation and enhanced evaporative demand. The second category is focusing on impacts. So things like soil moisture, evapotranspiration, and vegetation impacts or indices. It's important to note that these impacts can also feed back onto the meteorological drivers through land atmosphere feedback processes. And then in the third category is what I'm calling expert-driven composite analyses. So the prime example of this is the U.S. Drought Monitor. I'll finish on this slide by noting that with flash droughts, it's very important to look at rapid changes in these monitoring indices. So this is commonly done with a couple different approaches. One of these is by looking at percentiles. So, basically saying that an index must drop by a certain number of percentiles over a certain period of time. Or it can also be done using standardized change anomalies or things like the rapid change index. Okay, so the first data set I want to talk about is the U.S. Drought Monitor, which is a weekly analysis that is generated by a rotating shift of drought experts. There are various strengths and also a few weaknesses with the U.S. Drought Monitor when it comes to using it to monitor flash droughts. One of the big strengths of the Drought Monitor is that it is widely used both by researchers working on drought and also by practitioners that are trying to mitigate its impacts. It's also becoming very widely used by government agencies when developing different policies. Another big strength with the Drought Monitor is that it is an expert synthesis of numerous data sets that also combines impacts in order to make a best estimate of the drought severity. And this is very important because there are so many data sets available, so they put a lot of effort into trying to distill all those data sets down into a single weekly analysis. And because of this, it is easy to use. It's just a single analysis. It also makes it easy to understand. There are some weaknesses with the Drought Monitor. Ironically enough, because it is just one analysis, it's not always clear which type of drought is being depicted. So this can be especially a problem when short and long-term indicators disagree, or when conditions are rapidly changing. It also does have a little bit lower resolution than many monitoring data sets, especially if you're comparing them to satellite data sets. In the past, it was slow to respond to flash drought conditions, but that's definitely not the case anymore. The Drought Monitor authors are very quick to respond when conditions are rapidly changing now. It also has a relatively short data record, so going back to 2000, but that's in line with the most satellite data sets as well. So now I'm going to spend a few minutes here discussing some of the data sets that are used to look at the meteorological drivers of flash drought. The first of these is the Standardized Precipitation Index, or SPI. One of the main strengths of the SPI is that precipitation, of course, is a major driver of all types of drought, and that's certainly true for flash droughts as well. It can also be computed over a range of time scales, so from as short as a month up to many years. So it does make it a very versatile index. It does have a long data record, so it does allow for better estimates of just how severe are the precipitation departures, that you're seeing. There are several weaknesses with the SPI. One of these is that there are, very sparse in situ observations across many parts of the country, especially over longer time periods. And if you use radar-derived precipitation estimates, they can also be very heavily biased due to limitations in the algorithms that are used to convert the radar reflectivity into surface precipitation estimates. There are also gaps in radar coverage, like across mountainous regions, and then also tends to be lower coverage, for lower altitudes or elevations. It's also, so even though precipitation is obviously a very important driver of flash drought, it is not actually a direct indicator of drought impacts. And because of that, it can lead to misleading indications of drought severity, depending upon how that precipitation actually occurred. For example, there have been times where, regions will have very positive SPI values, but that happened because there were very intense thunderstorms, and much of that rainfall just ran off into area streams and rivers, which meant that the soil moisture was not able to recharge as much as might be as expected. So in other words, a flash drought can actually occur even when precipitation departures may not be particularly large yet. Okay, the next up is the Evaporative Demand Drought Index, or EDDI, which is used to depict anomalies in atmospheric evaporative demand. One of its main strengths is that evaporative demand is a key driver of flash drought onset and intensification. I often think of it as kind of like the accelerant for flash drought, where if you can have that be on a background of precipitation departures, it can lead to very rapid drought intensification. Like the SPI, it can be computed over a range of timescales. It also has a long data record that allows for better estimates of just how unusual the evaporative demand is across a location. There are several weaknesses with these kinds of tools. One of these is that it does have relatively coarse spatial resolution. And again, like SPI, it is not a direct indicator of drought impacts. So like the SPI, it can lead to false alarms sometimes because high temperatures by themselves may not lead to drought if precipitation is adequate. We could see that kind of scenario across the eastern U.S. During the summer, where some of our hottest periods with the most extreme evaporative demand also can be associated with widespread thunderstorms. Okay, so a different data set then has been developed to try to combine the strengths of the SPI and tools like EDDI are things like the Standardized Precipitation Evapotranspiration Index, or SPEI. The SPEI it combines anomalies in precipitation and evaporative demand into a single indicator. It can be computed over a range of timescales, and it too has a long data record. But like the previous two data sets, one of its main weaknesses is that, again, it is not a direct indicator of drought impacts. So to get more closely at, or to look more closely at the drought impacts, you can use tools such as the Evaporative Stress drought indicators. A couple examples are the Evaporative Stress Index, or ESI, which is computed using satellite observations, or CSER, which is computed using model reanalysis data sets. So strengths of these evaporative stress drought indicators are that they are direct indicators of moisture stress on vegetation health. In addition, the satellite-based tools, they do have very high spatial resolution. If you use Landsat, you can get all the way down to 30-meter resolution, but most of them are going to be within like the 1 to 4 kilometer resolution range. They can also be computed over a range of timescales, so as short as a week up to several months. There are several weaknesses with these kinds of tools. One of these is that the satellite-derived ET estimates can only be computed wherever the skies are clear. So this will limit their coverage. It does mean that you have to composite those daily clear sky ET estimates over longer time periods in order to get more complete coverage. But that then leads to a slower response when conditions are rapidly changing. In addition, the satellite-based tools have a shorter data record, basically starting from 2000 onward. And the last one here is that these kinds of tools are not useful indicators of drought outside the growing season. So another set of tools you can look at are vegetation condition indicators. So these are things like the Enhanced Vegetation Index or solar-induced fluorescence. The strengths of these indicators are that, again, they are direct indicators of the impacts of moisture stress on vegetation health and functioning. In addition, the EVI has very high spatial resolution. These data sets, though, do have some weaknesses. Again, like the ESI in the previous slide, they can only be retrieved when skies are clear. So this will lead to irregular updates, and they also have short data records. The last one is that SIF does have a very coarse resolution, which will limit its applications if you want to look at very high resolution flash drought monitoring. Okay, the last data set I want to look at here is soil moisture. These data sets can be obtained using model reanalyses, in situ observations, and also satellite retrievals. Now, there are several strengths with soil moisture. One of them is that soil moisture is a very important indicator of potential moisture stress. It too can be computed over different time scales, and if you use model reanalyses, you can get soil moisture data going back to 1979. So again, a very long data record. There are several weaknesses with soil moisture. One is that you do have very coarse spatial resolution. I shouldn't say very coarse. I mean, it can be very coarse at times, but sometimes it can get done maybe like 4 kilometer resolution if you use model reanalyses. In situ observations, those soil moisture observations may not be representative of conditions even a short distance away because of very large gradients in vegetation and soil properties. And likewise with model reanalyses, the coarse resolution of those model reanalyses means that the information provided in a single grid point may not be representative of any one location within that grid point because it is a spatial average. And the last thing I want to mention here is that whenever you use soil moisture, it's very important to use the appropriate soil layers when monitoring flash drought. It's generally not a good idea to use the topsoil. So, from 0 to 10 centimeters, because there's just too much variability within that shallow layer. And it's also not capturing the full root zone of the vegetation. Generally, it's better to look at like a 0 to 40 centimeter or 0 to 100 centimeter depth, because then you're actually capturing the root zone for the vegetation. Okay, the last slide here is showing the evolution of several of these data sets during the 2021 flash drought event across Montana. Now, because I'm short on time, I'm not going to go over this in detail, but I'm using this to illustrate that there are very large differences in the timing and intensity of the drought conditions across Montana, depending upon which of these data sets that you look at. And I'm showing this here because it demonstrates why it is so important to use multiple data sets to examine the evolution of flash drought events. I think you could reasonably argue that all these data sets are right. They're just capturing different aspects of the flash drought. And again, that just emphasizes why it's so important to use a multivariate framework when evaluating the evolution of flash droughts, and to look at how their impacts are cascading through the environment. Okay, so with that, I'll stop here and take any questions if there's time. Thank you.
Thank you, Jason. I think we do have time. I think we're ahead of schedule a little bit for a question or two. Fire away. Andy?
Yeah, thank you very much. Can you go back one slide? I love this picture because it shows how complex the situation is for flash drought. And as I was looking at this here, I'm like, well, how does one create a composite indicator that's objective to include all of this? Number one, this is a charge to the room. This isn't just a question for you, Jason.
Yeah.
And number two, is it better that we just try to interpret the situation as we would say through like the US Drought Monitor or other means to be able to put this all together and to be able to create a good monitoring situation for flash drought? So again, not just a question for you, Jason, but for everybody, because I think this is an overarching question for all of us. Thanks.
Yeah, I think there's a couple paths forward. One is to have objective tools to look at rapid changes in these indices, but then it still takes some human interpretation to really distill this down into realistic estimates of, is flash drought occurring, has it occurred, how intense is it, and then equally important to look at this across different parts of the country. This example is just Montana. I would expect that you might get similar yet different kinds of responses if you're looking at Alabama or Oklahoma or Wisconsin, for example. So there's a lot of research to be done yet.
Thanks. I really appreciate the presentation, and definitely really appreciate this slide. You mentioned, just the differences, especially in regionalization, and sometimes when I think about drought in terms of like extreme percentiles, flash drought, especially in the Southeast where I'm from, this can happen a lot more often than, I say, a 5 percentile event or a 3 percentile event. In some cases, a flash drought, depending on where you are in the state, could happen every 2-3 years. And so I think, what's your perspective on, you talked about a little bit in some of the introductory slides about trying to understand that, not necessarily from a percentile standpoint, not that's just, historic big drought, but these, maybe 20-year events, 1 in 20 events, 1 in 5 events.
Well, I think, so I think it's very important to also consider the climatological variability within a region. It's one of the reasons why I'm not a big fan of using percentiles to identify flash drought. Instead, I really like to look at standardized change anomalies, because by standardizing those changes, you're looking at, you're able to account for if a location sees these oscillations on a regular basis. So I think one could argue that if they have these oscillations as part of the climate, they happen every year, flash drought can't happen every year. So if you look at a standardized change anomaly, you could still then be able to identify, is this change truly anomalous for this region? And then if it is, it's a flash drought. Because you can't have more flash droughts than you have droughts. They have to be a subset of all drought events. So it can't be more than 20% of the time over a long enough time frame. And then again, try to account for the regional variability. That's my opinion.
Take one more if there are more questions right now.
We do have a couple on the from the virtual audience.
Sorry.
Can you all hear me?
Yeah, we can go ahead, Molly.
Okay, great. So one question from Jen Henderson is, I'd love to know how this type of complex data might be integrated with social data about decisions and observations of impacts. Are people in this room working on this kind of integration? And if so, can we share examples? So I don't know, Jason, if you have an answer to that, or if anyone else in the room wants to address that.
Yeah, actually, I have a couple comments on that. One is that we do have a couple projects where we have worked with farmers and ranchers to understand what tools they need to better prepare for flash drought. I'm actually working with a couple of people at Montana State, University of Nebraska. So, Jamie McAvoy, Sarah Church, Tanya Haig, looking at ecological flash drought in Montana. That's actually the basis for the results I'm showing here on this slide. But on a bigger picture, we definitely need to spend more time working with social scientists to better understand how these tools can be used by practitioners. I would argue that that's almost always forgotten. Most of the effort is put into developing these tools, and then we throw them over the fence. We hope that they get used. It's not a good approach. We have to spend more time actually working with people. So I think that's a great question. It's a great point that was made. Was there one more question?
There is one more virtual question. I think
Okay.
we have a minute. So the question is, there are large variations across different drought indices, or if there are, and they show different flash drought signals. What would be the strategy to decide whether a flash drought occurs or not? So looking at all of these, they show different things. So how do you decide if a certain area is experiencing a flash drought or not?
Well, that's a great question. I think it really comes down to a convergence of evidence approach, where the more tools, the more data sets are indicating flash drought is occurring, the more confidence you can have that it actually is occurring. It's the same it's the same dilemma that the authors of the Drought Monitor are faced with every week. Where you might have some cases it's really easy. You're in drought. You're in severe drought. But it's those edge cases or the situation where you're just falling into flash drought. They will always be more difficult to identify. But as more of the data sets are indicating flash drought, the more confidence you have that's happening.
Great. Thank you, Molly, for the online questions.
So Marina, did you want us to sit at the front then? Okay.
Yes.
Okay.
Thanks, Jason. All right, well, that was a great start. So next we have Hailan Wang and Andy Hoyle. I'm not sure if both are presenting, but I'm going to introduce both of you. So Hailan Wang is a meteorologist from NOAA's Climate Prediction Center, specializing in research and development to improve drought monitoring and prediction products. And Andy Hoyle is a research meteorologist at NOAA Physical Sciences Laboratory, who researches the processes, predictability, and projections of hydroclimatic extremes that can be used to improve outlooks of fire risk, drought, water availability, and food insecurity.
Thank you.
Take it away, Andy.
Oh, hi, everybody. It's good to see everybody again. Let me try to get myself acquainted with the screen here. All right. Well, as Dan said, I'm Andy. She's Hailan, and we are going to talk about flash drought prediction and predictability. So I'm going to go first, and I'll talk about predictability, and Hailan will talk about prediction. And just to address Marina's sentiments before, yes, what you said was perfectly acceptable. Thank you very much. And we'll get into that a little bit. Yes, we indeed need some priorities for predictability research and how we can better understand the physical system and apply that to a skillful prediction. Predictability in the simplest sense is the ability to accurately predict deviations from average. It's in the word, the ability to predict. Predictability is about understanding your physical mechanisms. It's about understanding the processes and what goes into the phenomena of drought so that you can use that to either enlighten what you're getting from a prediction system or to be able to piece together what's happening in real time. Now, what's interesting about predictability is the word, how you use it may be different from, say, how a meteorologist or someone who's predicting might use it. Now here, I'll just illustrate the point, and I give all the credit here to Mike Tippett and Tim Del Sol, who put this together, both world-renowned researchers, and they did this on climate.gov. So on the left, this is to illustrate lower predictability. Now, suppose I'm walking through the woods with my dog, Darcy. You know, he takes me on a walk every morning. He's a big boy. He drags me around, and we go on the same path every day. Well, because we're really not deviating very much from that climatological path, predicting that really wouldn't give us much predictability in the sense of like a meteorologist, like I would say. Now on the right, suppose we have a big bear come in. Now in our neighborhood, it's more foxes and coyotes than a bear, but it happens and we have to deviate from our path. If you were able to predict our deviation from that normal path, then you'd have higher predictability. So the name of the game here is to forecast and to predict the deviations from the average. That's what we mean by higher predictability. Now, how are we doing? I'll let you be the judge. You probably already know. The headline here is systematic predictability has been and continues to be elusive. And I'll illustrate the point here using skill scores. Skill scores are the technical term for how well are we doing. This is for the United States, and this is for precipitation forecasts for the contiguous United States. These forecasts began in about 1995, and when I last grabbed the data, it went through March of 2023. High key skill scores up to about 100. That means you got perfect skill. A -50 means you have perfectly imperfect skill. And a 0 means, well, you got nothing better than chance. The green bars right there indicate where we're at in terms of precipitation prediction skill. Now, noted that precipitation isn't the end all be all for flash drought, but this is just to illustrate the point here in terms of where are we at, what is our baseline. Well, as you can see, we're up and down. Sometimes we get a little negative skill, sometimes we get a little positive skill, but otherwise we're generally around the 0 line in terms of a 1-month lead forecast. I threw on there the 2-year running average forecast skill. That's in the orange line right there, and really doesn't show a whole lot of change over the decades there. You know, we're a little bit better than we were, say, around 2000, but otherwise we just have a slight bump up from there. So predictability, it continues to remain elusive. This slide right here, I don't really want to go into too much. It's just to illustrate that flash drought's really hard. And you guys already knew that. You can take every single aspect of the Earth system. You can take the land surface, the vegetation, the atmosphere, and how they interact and go between one another. And these are all important processes that are necessary to be able to better understand and to better predict flash drought in the future. Well, what are some examples of flash droughts here? I'm going to show 2 examples, 2012 and 2017. About how we handled those predictions in real time and what we were thinking at that time. Well, 2012, those were the olden days. You know, we were all walking uphill both ways, barefoot in the snow to school. And we thought about drought differently in those days. We thought about it as this slow moving phenomena. And at that time, Climate Prediction Center was issuing 3-month drought outlook. So the seasonal drought outlook. And you can see that's in the center panel. So this is from May of 2012, and this is for June to August of 2012. Their prediction, their outlook, was that of no drought development during that time. And part of the reason for that was because the NMME, the North American Multi-Model Ensemble, which was just in its infancy at the time, wasn't really predicting too much in the way of anomalous precipitation over the central United States. Well, as we all came to know, over the following 3 months, we dipped into exceptional drought. And you can see the drought change map there on the right from the US Drought Monitor. Now, this change map right here is over 3 months, and it's pretty extreme, but you can actually note if you go back just into the record that these big changes actually happened over the first month within there. So all of this to say an impactful flash drought that wasn't predicted just because we didn't have those outlooks at the time. Now, if you move on to 2017, we were thinking about drought a little bit differently at that time, though I would say that this drought and a few others that followed the Southeast drought in 2019 as an example kind of led us to be here today. But at this time, Climate Prediction Center, they had created a monthly drought outlook, almost as in response to the 2012 drought, and they did that in 2013, 2014. Now, in June 2017, the drought outlook, which is in the middle from May of 2017, indicated a little bit of drought development in North Dakota and South Dakota. And it's actually interesting because this was issued on the last day of the month. Had they issued this in the middle of the month like they did the seasonal drought outlook, there was no drought development forecast or outlook at that time, just because this flash drought was exceptional in its development. Now, why was there very little in the way of drought and drought outlook at that time? Well, the North American Multi-Model Ensemble precipitation forecast was actually for above average precipitation for the following month, May of 2017, or across much of the United States. So June 2017 in this context was supposed to be above average. So naturally, you wouldn't forecast flash drought. That said, you look at on the right and over the month of June of 2017, there it is. Big changes in the US Drought Monitor to the drought side. So again, that drought was not well forecast. Well, we don't have systematic predictability, so should we just throw our hands up and say, oh, we're finished, let's just go home and move on to do something else? Not quite, actually. We do have predictable windows of opportunity. And a window of opportunity, as defined by this paper in the Bulletin of the American Meteorological Society, are basically our subset of forecasts where we have higher skill, we have higher confidence in the forecast because we understand the physical mechanisms that are operating at that time that increase the risk of a certain outcome happening, whether it's a precipitation anomaly, a temperature anomaly, flash drought, and so on. If we can identify the processes and conditions that lead to these predictable conditions, we can potentially provide more useful subseasonal, seasonal, and seasonal to decadal forecasts. This is really the state of the science here. It's about trying to understand the situation that lead to increased predictability and how we can apply that to a more skillful prediction. So I'm going to illustrate two examples here. One is with the Indian Ocean Dipole and Southeast US drought risk. So this is really relevant to the 2019 Southeast US drought. So the Indian Ocean Dipole, I'm used to working on and researching in the context of African climate, but it turns out that it was very important to Southeast US climate and especially the 2019 drought. On the left are these positive Indian Ocean Dipole conditions. And what I did is just a very simple map from an online tool that we have at the Physical Sciences Laboratory to say, wow, precipitation tends to be below average when we see Indian Ocean Dipole conditions like we saw in 2019. And then you look on the right, this is from a paper that was led by Siegfried Schubert and colleagues, and Hyland was an author on this paper. And they wrote a very nice paper diagnosing the causes of this drought and linked it very closely to that Indian Ocean Dipole situation. Essentially what happened is the tropical forcing in the Western Pacific was such that we had a wave train, we had a cascading array of waves that moved downstream across North America and led to below average precipitation there. So this was a forecast of opportunity and was predictable. And then there are other situations like this one right here, where what I'm showing is the risk of extreme precipitation related to the El Nino Southern Oscillation. So again, from really the same simple online tool that we have at the Physical Sciences Laboratory, this is June, July, August precipitation extremes related to La Nina on the left and El Nino on the right. And what we see on the left is that we have an extreme dry risk related to La Nina in the Northern Great Plains. What that would indicate is that during June, July, and August in the Northern Great Plains, you would have an increase in the risk of drought and therefore flash drought. And on the right, you get the opposite. El Nino leads to an increased risk of wetness, which would therefore decrease your risk of flash drought in those areas. So these are the types of things that we're researching in the predictability community about how to understand physical mechanisms and apply that to a good prediction going forward. Now, this is my final slide here, so we're just going to transition and hand off. So I'll just kind of read here about some research and development and some opportunities. What we need to do is we need to identify new predictability sources from a physical basis, including that of climate change, subseasonal to seasonal drivers, and understand the representation of the known predictability sources in the dynamical models that we use. Because after all, we use those dynamical models to provide guidance, but we do have to try to interpret what the results from those models are. Dynamical model development, improvements in the model physics, data assimilation, especially over land. Land is an important aspect, especially during summertime in many areas of the globe, central United States being one of them. And then finally, statistical model development, adopting and applying novel prediction techniques and using them to identify predictability sources. So there are ways to create statistical models in a way to highlight those relationships in the climate that will allow us to understand and identify what physical mechanisms we should be focusing on. So with that, I will end, and Hailan will come up here and we'll move on to prediction. So thanks for listening, and yeah, I look forward to chatting with you guys a little bit more.
Good morning, everyone. I'm Hailan Wang from NOAA Climate Prediction Center. So next, we're just going to talk about flash drought prediction, as Andy has nicely laid out. Now, we all know that the prediction scale for flash drought is quite limited. So this just naturally raises the question of why. Why is flash drought so difficult to predict? And also importantly, whether some of the existing flash drought outlook products, for example, the CPC monthly and seasonal drought outlooks, which respectively provide the forecast guidance at the lead time of 1 month and 3 months, whether they're adequate or appropriate for flash drought prediction. And if they're not, whether we should develop new products specifically for flash drought. So for the first question, why flash drought is so difficult to predict? Well, this would to a large extent relate to the flash drought themselves, because a considerable portion of the flash drought events have this limited predictability. Flash drought is typically induced by this sustained precipitation deficit and heat wave events. And the typical processes that will lead to these sustained precipitation and temperature anomalies typically would have this limited predictability. So basically, a considerable portion of the flash drought events would have this, would be presenting as a low ratio signal to noise ratio problem. And on top of that, the forecast tools that we're currently using are not perfect. It is pretty well known that the dynamic forecast system that we use, they contain this considerable variety of model biases, and these model biases could potentially prohibit these forecast systems from properly capturing the sources of flash drought predictability and their subsequent impact on the flash drought evolution of land. And also with regard to land surface processes, as Andy has pointed out, vegetation is an important component of the flash drought phenomena. But currently, as far as we know, some of the existing land surface models are still challenged and also limited in realistically simulating this dynamic vegetation process, basically realistically simulating this dynamic interaction between vegetation changes and land surface state. And additionally, the statistical forecast tools can be helpful in complementing dynamic forecast systems. But currently, so far, the development of these tools are in infancy. So given that the flash drought, considerable portion of flash drought events have this limited predictability, and also flash drought itself is present as a rapid evolving phenomena, our recommendation is that it is necessary to develop the forecast product specific for flash drought. So here are our recommended properties for this forecast product for flash drought. First, the product need to specifically target flash drought. It should directly tell exactly where and when flash drought is going to occur. And in terms of flash drought phases, it is preferred that the product can not only predict the flash drought onset, flash drought development, but also the subsequent drought evolution, including drought persistence and termination, together with other necessary characteristics such as drought severity. And the product is preferred to be probabilistic to contain this probability or uncertainty information to facilitate the user decision-making. And in terms of lead time, considering that different flash drought events might have different predictability, so lead time should range from week 1 to week 2 and up to subseasonal. And the product needs to be produced and issued weekly or more frequently in order to capture flash drought as a rapid evolving phenomena. And additionally, the product is preferred to be aligned with sector-specific flash drought impacts in order to make connection to user needs. And lastly, the visualization and dissemination of the product need to incorporate social science, need to incorporate the feedback from a variety of end users and stakeholders with different background, so that the product can be easy to understand and straightforward to interpret. So even though the flash drought prediction is relatively new, we have already made some good progress on this in this arena. So here just list these two products, the NOAA CBC Rapid Onset Drought Tool, and also this MRCC Flash Drought Risk Tool. These tools are listed at NIDIS website. These are the current existing flash drought products that specifically target flash drought, and both products provide the forecast guidance at 2-week lead time. So the first tool developed at CBC, it just used the methodology that CBC has been using in the production of CBC monthly drought outlook, except that the forecast target is flash drought and at the 2-week lead time. And second tool just proceeds methodology-wise, proceed by applying the machine learning methods to dynamic model forecast, and the effort was supported by NIDIS. And additionally, we have a variety of supplementary products, and these would include the forecast of flash drought related variables such as precipitation, temperature, soil moisture, eddy, and so on, together with the monitoring of the flash drought early warning indicators. So in order to connect these supplementary products to the actual flash drought prediction, the user need to have a good physical understanding of their connection. And actually, some of these products are going to be on display this afternoon as a tool cafe session. So feel free to stop by if you're interested. And our effort of developing flash drought prediction product does not stop here. And in fact, currently there are some ongoing extensive effort on developing new flash drought outlook product in order to better address user needs and stakeholder needs. So here just use the ongoing effort at CBC as one example, currently under support of NIDIS. CBC folks are currently working on developing this probabilistic flash drought outlook. I'm not sure if I can, but anyway. So for this product development, it has this dynamic component and statistical component. And currently our emphasis is on dynamic component. So basically our development just start from this subseasonal dynamic forecast. And because these forecasts are subject to the model biases, so we will do this post-processing, which include bias correction and calibration to improve the skill and reliability of the meteorological forecast, especially those for precipitation and temperature. And then we would produce the dynamic forecast for land surface variables by driving land surface model of land with a post-processed meteorological forecast. And afterwards, using the dynamic forecast for the list of meteorological and the land surface variables, we will be able to produce a dynamic forecast for various flash drought indices, which include but not limited to what is listed here. And our next step is just to objectively blend the forecast for flash drought indices to produce integrated flash drought forecast. This is just really meant to produce a user-friendly product. And lastly, we would apply social science to finalize the product visualization and dissemination. So basically for each of these steps would involve substantial investigation and also involve substantial collaboration with external partners. For example, for land surface model component, we're currently collaborating with NSAP EMC on incorporating their latest and greatest land surface model. And for the last step, social science, we recently started the conversation with our existing social science collaborators at the University of Minnesota. So lastly, we're going to talk about these prediction opportunities. So really, what can we do better to improve flash drought prediction? This also relates to the gap between the operational prediction needs and flash drought research. Dynamic forecast systems, obviously, and improvement to forecast initialization models can be helpful for flash drought prediction. And in particular, when we have any new research findings on the sources of flash drought ability identified, it is essential to turn to the operational forecast system and see to what extent these sources can be well captured. If it turns out they are not well captured, then we need to pinpoint a specific model process that need to be developed, and then communicate with the model developer to improve that process. Statistical post-processing is important because the forecast of flash drought onset and development critically depend on the forecast scale for precipitation temperature. Some of the land surface models currently are not performing well in related simulating vegetation process. They need to be further improved in order to be applicable for actual flash drought prediction in terms of vegetation. So this is the last slide. Statistical tool development, especially if this effort does not take too long time, then can be really helpful in complementing dynamic forecast tools. Flash drought blends, it's just kind of echo what Andy just pointed out. It is, for this, at least for both not only monitoring, but also for prediction product, it is important for us to perform this blend to make the product user-friendly, because not all users would really have a good understanding of different flash drought indices, how they may differ from each other. So I need to find some way to integrate all this information and produce a straightforward and easy to understand product for user to use. And lastly, climate change. We know climate change has been modulating and will continue to modulate the characteristics of flash drought. Then how does climate change affect subsequent prediction of flash drought? So any new research findings on that can be helpful. Thank you.
Thank you, Helen and Andy. I think we do have time for one or two questions. I'll start with Mark.
So sort of a two-part question for Andy. On that graphic, that the next to last slide that showed the summer follow June, July, August, I believe it was for in the Great Plains sort of region. First question there is that for the summer following onset or during development? And secondly, have you looked at any of what we had here, which is kind of rare, this back to back to back La Nina? I know, you see back to back El Ninos and La Ninas splattered around there every once in a while. If that makes any difference in the drivers. So sort of a two-pronged question. Is that June, July, August following the winter? And then how does that come into play when you've got something like this triple header? Thanks.
Can you confirm? Now you can hear me. Oh, wow. Now I'm loud. So yeah, back to back to back, triple dip La Ninas, they imprint the ocean a little bit differently than just a 1 year La Nina. So every time that you have a La Nina, you have a little bit of a change, say in the Western Pacific Indian Ocean, which can then modulate the La Nina response at a later date. So that's one thing to consider. Specific to the Great Plains in the central United States, I don't know the answer to that. I'm not aware of research that's been done for triple dip La Ninas for the central US. I know there's some work that's been done on 2 year La Ninas, but they're more in the context of like cold season rather than warm season.
And I think we're gonna move on to stay on time, or one more maybe, more questions?
I think there might be a comment in the virtual audience.
Yeah, there actually is a question now. There was a comment just about some Midwest events, but I'm going to just focus on the question. So actually there's two quick questions if we have time. For Andy, do we have a rough sense of which aspects, so the initial condition versus model process versus the chaotic, unpredictable nature of the system, what contributes more to the current inadequate model predictability?
There's a couple of different ways to interpret the question. I'd love to talk to that individual. Please send me an email offline. The chaotic nature, when we're making a forecast, that's what's polluting the forecast. We don't necessarily have predictability of it because by definition, it's chaotic. What we're trying to do is we're trying to isolate the signal within there, the signal coming from a slow varying process, like the El Nino Southern Oscillation, or what I illustrated with the Indian Ocean Dipole. I know there's a colleague of ours who's going to talk about the Madden-Julian Oscillation, which potentially, because of its slow varying nature and its ability to affect the climate over multiple weeks at a time, could do the same. So really what we're trying to do is we're trying to isolate those instances where we have that, whether it be within our own physical understanding or whether it's in the model. In terms of the separation of the initial conditions versus some other processes, those are initial condition processes that will follow along, but because of their slow varying nature, they therefore make the future weather and climate predictable, say on sub-seasonal timescales and seasonal timescales.
And looking at the time, do you want to save the last question to go on to the next presenter?
Yes.
Yeah,
Okay.
we're going to move on, and then we're going to have plenty of time for discussion, and we can talk more about prediction at that point. So we do have one more talk prior to our break, and this will be a virtual presentation. Looks like I think Amanda's there. So next up is Amanda Cravens. She'll be talking about flash drought impacts. And Amanda is a research social scientist at the U.S. Geological Survey Forest and Rangeland Ecosystem Science Center. So welcome, Amanda, virtually, and take it away.
All right, just checking that everybody can hear me and see slides.
All
right.
right, good.
Yes, you're good.
Perfect. Well, thank you for having me, and thank you for giving me the opportunity to join you, not being there in person, although I'm sure it's a beautiful day in Boulder. So I am going to be talking to you about flash drought impacts, the things that we know and some of the things that we don't know, because there's quite a bit that we don't know as well right now. So as you will see in the slides, this is work that draws on quite a bit on work from a paper that Jason Otkin led. I think you've heard from other pieces from that paper in some of the earlier presentations. So digging right in, I think that this quote will be familiar to many of you, if not most of you in the audience. But I wanted to go ahead with apologies, although hopefully he would smile about it, to Kelly Redmond. Go ahead and ask this question to start us off. Does flash drought occur if there's no human to record or experience it? And particularly to kind of frame this, thinking about what is different about flash drought than conventional drought that we know quite a bit about at this point. So some drought impacts, and these are just drought impacts of conventional drought that we know that we talk about in general over a long period of time. And, you know, you may think about one of these, you may think about a lot of these, depending on, you know, what point of view you're bringing to this challenge. Water supplies, vegetation, economic costs, wildfire risk, crop yields. We could go on and on here. Where I think the really interesting question for this workshop is to then ask, what is unique about flash drought impacts? And the answer that the team came up with in this paper, and I especially want to acknowledge Tanya Hay, who really was helping me think about the flash drought impacts, was impacts that are different or a different magnitude because of that quick intensification of drought. And so, for example, you know, you may have calls for irrigation water at the same time happening, and that may push your system beyond its ability to meet demand. Or you may have different magnitude of impacts because of when that drought intensification period happened. So examples, and we'll get to agricultural impacts in a second, but when flash drought emerges early in the growing season, you have sensitivity from crops that might not happen if that same flash drought emerged much later in the growing season when crops were less sensitive. Or flash drought creating high fuel loads that can increase wildfire risk. One of the examples the paper mentioned that has a lot of relevance to those of you sitting in Boulder, Colorado, was the Marshall Fire that happened a couple of years ago and has some link to earlier flash drought that year. And then, you know, this other point that I think is really important to think about is, you know, in other cases, flash drought may lead to impacts that are not actually that different from conventional drought, at least as experienced by certain sectors, certain communities, or certain regions. So going back to that first slide, all right, this gives us some flash drought impacts. So water supplies that have diminished rapidly, decreased vegetation productivity that's changed quickly, wildfire stress or population declines, again, because of that very quick change, economic costs, and what may be unique is the fact that farmers had no anticipation or ability to adapt. Unanticipated increased wildfire risk, reduced crop yields after part of the year was looking okay. So again, that change based on either when or the nature of the rapid intensification. These are some of the photos from that picture I wanted to go ahead and share with you. We've got spring wheat in central Montana. We've got winter wheat in southeastern Washington, grazed pasture in central Montana, and a grass fire in central South Dakota. Just some pictures of what we're actually talking about made real. All right, so stepping back and saying, what do we and don't we know about flash drought impacts? Well, we know a lot about agriculture impacts. There was a very recent paper by Walker and Van Loon in Science, and the way they summarize this is, to date, research has dominantly and logically focused on agricultural impacts. There's a Christian et al. 2019 paper that looks at timing of flash drought occurrence in the United States. You can see that on the top left. You do see quite a bit of emergence across July and August, more, and then some in June and September, less in the rest of the season. That makes sense because drought, in general occurs in those seasons. But looking at just the temporal changes in the continental United States, a similar kind of analysis looking globally of flash drought occurrence sort of spatially across the world. These are some hotspots. This is a Christian et al. 2021 paper on the bottom right. And then Hunt et al. 2021 did an analysis of a flash drought that occurred in the Ukraine in, oh my goodness, I've just forgotten if it was 2010 or 2011. I think this was 2010, that is linked where the winter wheat yields decreased and actually have cascading economic impacts across the world, because the decreases in winter wheat then are affecting prices and global supplies for wheat. And there's actually been suggestion that this was linked to some of the unrest around the Arab Spring. Now, there's a number of other impacts that we know a lot less about for flash drought. Hydrological impacts and how these eventually impact water supply. Part of that is that we tend to look at impacts across a water year. So actually separating out the impact of flash drought can be challenging. Ecological impacts. So we do know there's a link to soil moisture and higher evaporative demand, but what that actually means for the health of vegetations, ecosystems, and wildlife is less clear right now. Social, economic, and human health or psychological impacts outside the agricultural sector and how those are unique to flash drought, at least from what I've been able to find, has received almost no attention. And I think that this is particularly interesting because we know from just the way that people make decisions and process risk that abrupt changes are going to be different and potentially more damaging than things that people have more time to prepare for. So I think that this sort of human health, psychological, social impacts are a particularly interesting place for more investigation of flash drought specific impacts. And then there's the question of variability across time and space and sector. So how the impacts vary by region, that kind of analysis that we saw for the agricultural impacts, but doing that for some of these other sectors. And then that temporal, how these impacts are different depending on when in the water year or growing season a flash drought emerges or intensifies. And then how the impacts are different depending on how long the flash drought conditions persist, or sorry, how long drought conditions in general persist after the flash drought. I'm joking, but not joking. If there's anybody who's looking for a social science dissertation topic, there's a lot of work that could be done here that would be really interesting. And the final point that I want to make is around the assessment of flash drought. And I think that this really involves being precise about exactly what we're interested in assessing. So for some of those impacts in some regions and sectors, it is going to be less important to assess the flash drought impact than the overall drought impact. And in those cases, the assessment methods that are tried and true, that are generally retrospective assessments at the end of the drought period, are going to work just fine. Conversely, when we are really interested in teasing out that impact of the intensification period, and those unique impacts of flash drought compared to the conventional drought that follows it, then we're going to need to develop some methods that maybe are newer or less tried and true. That might involve social media, that might involve crowdsourcing, or that might involve other rapid assessment methods. So that is an overview, and I am happy to take questions.
Thank you, Amanda. I think we have plenty of time for questions, both online and here in the audience.
All right, and that Ukraine drought was the summer of 2010, Western Russia. I'm sorry about that. That was one of those, just it escaped my mind.
No problem.
Why it was in front of me.
We do have one audience question here.
Yep, there it is. Okay. Hi, great presentation. Thank you so much for the information. I think it offered a lot of interesting, at least personally, reflection on, as you mentioned earlier, the prevalence of agricultural drought focus in the world of flash drought. You can even see that in the conversation that was, or the presentation that Jason had earlier about various indices and using vegetation stress and, satellite imagery and stuff like that. But I'm curious, along with that, it almost seems like, as was presented in Jason's presentation, and I must admit, I think of it the same way, flash drought being its own separate category of drought alongside hydrologic, meteorological, agricultural, socioeconomic. If rather it's just a different manifestation of those droughts. And so if so, would, let's say, a hydrologic or like a meteorological or a climatological or an agricultural, whatever, droughts have various different influences, indices that might be predictive of that. And yeah, I mean, things along those lines. So I guess, I don't know if there's a question in there. I guess I'm curious amongst not only yourself, but also the previous panelists as well, or presenters as well, thoughts to that effect, as far as how multifaceted and complex this could get if we're all of a sudden having to think about different influences and impacts for different types of droughts, flash droughts.
Well, I certainly can give you my point of view, but I think you may get different answers from the other panelists. I'm really interested to hear what they have to say. When I think about these names we have for different kinds of drought, I think they are as useful as the reasons we have different names is for two reasons. One is they allow us scientifically to describe what's going on, and the indices like you're talking about with Jason's presentation, and they are names that can help our practitioners describe what they are seeing and why it might be different from something else that is named differently. So I guess from my point of view, that the way I've understood the science, but this is where I defer to those who are much more technical, the distinguishing feature of the flash drought has really been around the fact that it rapidly intensifies. So to me, that means that rapid intensification could then lead to impacts that would overlap with different kinds of drought. It could lead to impacts that propagate into the hydrological system or propagate into the agricultural system, certainly propagate into our socioeconomic system. Exactly how that happens scientifically, I think we might debate. But the second piece of that around the stakeholders, I think we probably need to really tease out some of these impacts to answer that. Is this a useful distinction for people who are experiencing this? I think that with agriculture, we've seen it is. What happened on the Northern Plains in 2017, giving it a name allowed different kind of preparation going forward for some of the drought task forces, for some of the agencies. It allowed people to say, oh, we missed this because this was a different kind of beast. It needs a different kind of name. Whether that is different in the water supply arena, whether that is different when you're talking about sort of human health impacts and public health, that is less clear to me right now.
Thank you.
All right, do we have more questions from the audience or online?
No questions from the online audience right now.
Okay, we do have one more here.
Thanks, Amanda. This is Mark with the National Drought Mitigation Center. I know you worked with Tanya in my shop a lot on this and others. This is probably more a little bit of a comment than a question, but I think the fundamental crux of this issue is we don't invest in impact collection like we should. We don't have a baseline of what it looks like now, let alone under a changing climate. Makes it a moving target. And it's already challenging enough without that and the interplay between the different types of droughts and the impacts. That said, we've been trying to plug away at it, sort of stopgap measures through the drought impact database. The database we stood up as a first of its kind in 2005. That continues on. And then more recently, and hopefully more encouragingly, you mentioned, Amanda, and I agree, like the Condition Monitoring Observer Report Network, coordinating and collaborating with CocoRa's that they can enter in drought impacts, and then scrubbing Twitter or Mastodon or whatever that next platform may be. So I think there's a lot of work to be done in this area. You're right, a lot of research, but I'm hoping that and we are seeing some in the research community of trying to tie impacts to indicators. So hopefully when the next one comes around, we're doing that more real time versus retrospectively. At least that's the hope. And I do have another question for Highland if we're taking questions for this panel, since they're sitting up there before the break, or just Amanda right now, since I have the mic.
Well, we got 2 minutes until break. So let's just first see if there's any more questions for Amanda. And if not, we can quickly go to Highland. We do have another question for Amanda. So if not, Mark, we'll come back during the discussion.
Of course, it would be
Mark will
Meredith.
have another chance. Is
Is
this
this on?
working?
Oh, I can just talk this. Hey, Amanda, this is Meredith Nidus. I'm the regional coordinator for the Southeast Drought Early Warning System, and you're going to hear a little bit about the work we're doing right now tomorrow. But I just wanted to make a comment. I mean, I had a little bit of an epiphany with your talk, because we actually did a technical discussion on flash drought in the Southeast context, and we tried to tease apart, okay, what impacts are felt during a flash drought, but then we pushed people to really think, is this any different than a quote unquote regular drought? And there was a huge struggle to make that separation. But what I'm hearing from you was not so much the how do we distinguish the impacts of flash drought, but more of maybe we should be talking about the why. And for you, it was, it could maybe change the messaging that could influence response and decisions, et cetera. And I didn't really make that connection before, but I just wanted to know I just wanted to share that with you and see if you had any reaction. Thank you.
Yeah, Meredith, that's really interesting. And it's really encouraging to me that what I'm saying makes sense, because I have not had a chance to work directly with practitioners or around the flash drought piece. I've done it, with some conventional drought work, but it makes absolute sense to me. I think that my argument here is that there will be cases where the fact that it's a flash drought absolutely matters. And then there will be other cases where the fact that the drought came on quickly is less important than the fact that the drought lasted for 5 months and reservoir storage ran out, or whatever the full drought period looked like. And I guess I think that in terms of messaging and in terms of thinking about overall impacts for a particular community or a particular sector, I think we maybe need to start with that question of, in this case, is it more important that it started with a flash drought, or that there was a period of intensification in the middle of it? Or is it more important what that overall, say 5-month period of drought looked like? And I think that's where our communities can tell us what their experiences are like, and which we need to be focusing on in a particular situation.
Thank you, Amanda, so much for that and joining us virtually. We're going to go to our first break now for 20 minutes and we'll reconvene at 10:40 to wrap up this first session. So thank you, everyone.
Good morning again, everyone. Can we please start to return to the plenary session room and the virtual plenary room? Thank you.
All righty, so let's continue with our State of the Science session. So our next speaker here is Mark Svoboda. Mark is an associate professor and director of the National Drought Mitigation Center at UNL, who co-founded the U.S. Drought Monitor and is credited with coining the term flash drought. And so you can take it away, Mark. Thank you. Thanks, Dan.
Thank you. Great to be here. Appreciate the opportunity and invitation. I think I could have shortened this title. Really, this in a nutshell is now what. We've heard a lot about impacts and tools and monitoring, early warning, prediction. At the end of the day, the now what is what do you do with it? How do we make it usable? How do we get it into decision and policy making? Admittedly, in terms of flash drought, this is relatively nascent. But what my hope is, in working in this field for 30 years now, is we can use the opportunity that drought can just be, oh, we'll deal with it later. It's going to come on slowly. It's going to take months or years to develop. And this paradigm change is needed when it comes to drought. And I think I've already seen that in our work on the ground. Communities, counties, water districts, et cetera, look at this differently now. FEMA, multi-hazard planning, natural resource management. If drought can come on quickly like this, now we need to think differently about how we address it and deal with it. So obviously our venerable leader, Dr. Akin, already spoke to you all here, and my colleagues here. So a lot of what I'm talking about is in this paper, but a lot of it is informed through other work and other efforts, even on the international side. So what we're trying to do here is move people from the right to the left, not politically, but in this chart. We're trying to get people to stop thinking it only about a long-term, slow onset disaster. We're always going to get caught with our head in the sand if we continue to do that, and that's what we'll continue to do. The founding director of the center, Dr. Wilhite, affectionately termed this the hydroillogical cycle. If you've seen that cartoon, it's pretty famous. It really talks about apathy and not dealing with it until you're in it. There's also a very famous line from Pirates of the Caribbean that alludes to this. You don't realize you're in a nightmare. You think you're in it. With drought, it kind of behaves the same way. It's like these nice days turn into nice weeks, and then all of a sudden, now the impacts come. But you could have seen that coming if you're really monitoring it day to day, week to week. And even if I had a perfect 100% skill on forecasting, you need a combination of both the monitoring and the forecasting to show where, how intense, spatial extent, and impacts. So that's why when I work globally, they always think early warning is just forecasting. And really you need both pieces, particularly with drought, I might add. It's so much more challenging in the cascading systemic nature of the way drought behaves. So we're hoping this helps change that mindset. Now, if you've read that paper, one of the key graphics, which I think sort of is a nice illustration of what, I mean, there's a lot going on here, but this is really the reality of it. We started thinking about how to display this, and I'm sure Molly's laughing online. How do we distill all of this into what a drought early warning system is? But pay attention to that center core. That center core looks at scale. It looks at stakeholders. There's a lot of players involved in dealing with drought, because unlike other hazards, if you think about it, drought potentially covers millions of square miles and can last, days, weeks, months, decades. It's so much different to deal with when it's always there. It doesn't just come and hit and go. The footprint is potentially large, both spatially and temporally. So this is our way of trying to show what's involved in coordination of an effective drought early warning system, not just during drought, but in advance of drought. So again, bringing the monitoring piece into the system, where's the hook for flash drought? And that's changing the idea of our paradigm that it's only a slow onset disaster. So this sort of system becomes even more important when you are in a flash drought development situation, because if that system's working correctly, at least they'll be on top of looking at the indicators and briefing their respective leaders, whether that's the governor or some other entity. So luckily, you know, and Jason showed some of these tools, but just in general, alluding to the emerging state of the science, augmenting our in situ networks, which will never be dense enough, particularly here in the West, right? So how do we augment those with these new breed of tools that can help us better track flash drought? You know, I look back, I forget if it was Andy or who showed earlier the 2012 drought. You know, if we went back and made that map now with the Drought Monitor and had those tools that I'm putting along the bottom here, you know, you would see a whole different map. It just shows what sort of R&D came out of that 2012 drought, supported by the NIDIS Coping with Drought and the NOAA Climate Program Office over the last 10 plus years now. Even newer tools are on the way. I'm just showing a couple that we're working on. We've already heard Climate Engine alluded to, which is gone through some nice evolution as well. And there are many, many others. So I don't mean to leave anybody out, but we've taken advantage of machine learning and ways to find ways to combine indicators to understand regionality and seasonality. And there's been a lot of effort by many of you in the room on that as well. And I hope to learn some new things here this week as well. But, you know, our flash drought index there in the bottom right is one we've been working on and pseudo operationally last growing season, and now more formally now this growing season, to hopefully provide more tools for the authors, at least in the case of the Drought Monitor, to put into their toolbox. So again, just to reiterate, I you know, drought early warning is both. It's not just forecasting, it's both. And I think we've covered that here in this panel quite nicely. Jason alluded to the multivariate approach very nicely, that no single driver typically is the answer. Now, it can be for very specific applications. You know, if you're a water utility that's based solely on a water level of a particular groundwater reservoir stream, okay, that you know, you're tuned into that. But understanding what might be coming, whether it's a forecast or through monitoring that might affect those levels, that's still important. Even in the Drought Monitor's case in the West, where you might think it's not as applicable, if it's used correctly, it can be. I think some of this is education, but it can also sort of be a precursor to potential demand. If we're showing it as we should at the time as a current snapshot and not waiting for the impacts because we know they'll come, then we can do a better job of using it as an early warning tool. And in general, flash droughts, I think, can be this new torchbearer to inform decision and policy making. The tools that are evolving out of these research programs can hopefully have us not get caught sticking our head in the sand. So I'll just wrap up with a couple key points here. I've said this a lot ad nauseum. I don't think it's a tool set issue. I think it's a mindset issue right now. And that's education. And all of you can play a role in that with your respective stakeholders. And that's something that, you know, that'll be continual. That won't be solved by the time I retire. And I think Jason captured pretty nicely, you know, and I feel the same way. There is no universal definition for drought. Why would we expect there to be one for flash drought? Right? It's in the eyes of the beholder. It's in the eyes of your application. So what tools can we provide to best address it for you? And just making you aware of what's out there. And I think there's probably a lot more out there that people are not aware of. It's just proliferated here, right? So the whole idea here, though, is to get this in front of groups that work with multi-hazard planning, water plans, comprehensive plans, climate change adaptation plans, and of course, standalone drought plans. It's the whole continuum. And in fact, over the last 5 to 10 years, we've seen more people. My first 20 years was predominantly state level, you know, top down. US doesn't have a national drought policy. but the states, sort of being the sovereign entities that they are in a way, controlled that process. But in the last 10 years, we've seen a lot more demand for drought planning, scenario assessment, things of that nature, right down to the individual producer, ranchers and producers, certainly at the community level. And now we're seeing a lot of money thrown at drought planning with the bill and IRA, recent bills to throw a lot of money into some of the federal agencies. I hope that trickles down well to the states in the next year or two, on drought specifically and climate change adaptation. So drought fits into that niche, in my opinion. All right, so with that, thank you very much. If I have time for a question or two.
Okay, thank you, Mark. You guys hearing this? Yeah, we do have time for a few questions. Anyone in the audience here, or do we have any questions or comments online? Might get off easy, but Mike has a question.
Yeah, looks like we have one question online.
Mike, why don't you go here and then we'll go to the online question.
You're coming, Mike.
One button and I pressed it.
Here, want to trade?
Okay, I'm sorry. In your upcoming tools on your flash drought outlook. Sorry, I'm mangling the name. I saw the word objective. So I'm wondering, is there input, subjective input, like there is in the weekly drought map, as it's called? Is there subjective input, and if not, is there a place for it? I have my own opinion that people probably won't share, but is there a place for it, for the subjective opinion? Can that act fast enough? That's the question, I guess.
Okay, the short answer is it's primarily ML based. It isn't done like the Drought Monitor, if that's what you mean. There isn't an author drawing those lines on that map. So are we determining, is anything truly objective? Depending on the approaches you use, I think that's a misnomer. We're determining which indicators are in the pool for it to analyze, to look at those relationships, right? But then after that, at that point, sometimes the issue is, what's your truth? What are you comparing it to? If we're trying to compare it to something that's going to show drought quicker than anything else we have, that can be a problem to see, okay, what do we ground truth it against? So we're going through those issues like any other research to operations sort of product, but the bottom line is that is an ML based product. Is it fast enough? Most of those indicators in that FL blend and that flash drought blend are very short term nature. A lot of these are you're well inside an 8-week period. We're not out there. At the short term blend, we go out to 6 months, which was a traditional cutoff line of the SNL on the Drought Monitor map. That was 6 months. Greater than 6 months was sort of long term hydrological. Less than was short. This brings it down well subseasonal, down into say indicators from 4 weeks out to 12 weeks. Yeah.
All right, thanks, Mike. I think we had a question online.
Yeah, we have a question from Brad Rippey with the USDA. What do we do when no single indicator defines flash drought, but the audience demands a definition? In the case of drought in general, no single indicator provides an adequate definition, but the US Drought Monitor satisfies the audience.
Is that a question, Brad? Brad, you're supposed to be here and ask that to my face.
Rhetorical.
Yeah, no, I think, that the short answer is convergence of evidence, right? Does one indicator usually enough to cry wolf that you're going to put it out there on the line that, let's do this. Who's accountable to do what and when, which is the key to triggers into planning and policy. So again, I think it's a multivariate approach. And if I see just one
But let's say I see one and it's really resulting in a lot of impacts, perhaps I would be swayed if I was still doing the map, but I haven't had to do that for 6 years now. So I think it's all context specific of the situation. What were the antecedent conditions? Like right now, it's been really cool, but we've been extremely dry. You heard about the pileup in Illinois. We've got these massive dust storms. Everyone thinks that was solved with all the conservation efforts from the Dust Bowl years into NRCS. And it still shows you there can be a problem because of timing of planting. And so, you know, that matters too, I think, in the big picture. Do you have a question here from Kansas?
Yeah, we have time for another one. If you can go up to the mic, please.
Yeah, great presentation. And I guess I would maybe highlight, at least from my personal perspective, I am looking at things more from the policy framework side of things as well. So I really appreciate that you brought up kind of the BIL, IRA mindset when it comes to some of the drought opportunities that could be there. And I guess this is maybe sort of a question for the group as a whole, as we're thinking of the things or the context of these next few days. If there are any sort of, I guess, compilation of resources or areas of focus, which the collective drought community could look to focus efforts when it comes to either those BIL or IRA opportunities, as well as Farm Bill. It seems like Farm Bill could provide some opportunities there as well. So I appreciate you bringing that up, because that's one of the areas that I'm interested in kind of getting information and expertise from those that are here today to help align kind of I guess a collective approach that might be on the horizon, or at least potentially available for some of that coordination there. So I appreciate you bringing that up.
No, I appreciate your comments. Very relevant and timely. I was just on the Hill last week speaking with various committees within the House and Senate side about some of those issues. And I think the opportunity here, you know, this is a relatively tight-knit community in the drought world, right? You know, there's some new faces here, but in general, and they're very welcome. You'll find it a pretty receptive community to that. But where I'm going with that is I do think we need to oftentimes think outside of just our sphere of influence. What's the cascading impact? What's the transboundary impact across these geopolitical borders, so to speak? Drought doesn't care about borders. So how do we tap into some of those things? Might be some unique opportunities to think more broadly and beyond just your local sphere of influence. So I would totally encourage that. I hope you do take advantage of these funds, because, you know, they're not always going to be there, as we know. This is cyclical. Thanks.
Hi, Mark.
Hi.
Quick question. When you have all these different indices that you look at, as that one slide showed, of all those different parameters you have listed across the bottom, how do you, when we're looking at that from an operation standpoint that we're in, which do you weight more to one or less to another? Is there a methodology that you've developed to weight those, to give you a blended example of all that?
Yeah, those examples I showed you were individuals, primarily satellite derived or modeled. In the case of the new blends, like the new Flash Drought one and the new short-term and long-term blends, and some of the other, a ton of people here probably in the room working on these composite drought indicators, you can use machine learning to determine those weights, either supervised or unsupervised. You can just let it go and it sort of learns from looking retrospectively. Then do you trust it? There still needs to be a vetting, in my opinion. I mean, I have a jokingly at the Drought Monitor forum and at the Bureau of Reclamation, I've been there the last two of the last 3 weeks in Boulder City, is rise of the machines. You know, I was teasingly calling it DroughtNet. So how much do you trust then? Is that the only answer? No, I think somebody else mentioned you do need some human interpretation, but we can do it both ways. Expert judgment. I don't like the term subjective. I mean, these people, it's like a weather forecast office or a climate prediction center. They've got an ensemble suite of products. They look at that and they have a confidence level based on the convergence of evidence. And I think that's where our role is to, hey, we had this permeation on LDAS forcing recently, causing a bias issue in some of our products. The human element can say, okay, I'm not going to look at those this week until these get back in line. We had the big solar flare that fried some satellite data feeds. I have a gap of an input now, or two inputs into my CDI that I can't use.
Now what? So we have to be flexible and nimble, and that's where the human element comes in. Thanks.
Right. And then to follow up with that, just one
we'll
other,
have to-
hold on, just one more question.
Gotta move on.
I know, but I
Okay.
got one more question before we go. So then how are we actually, how is the drought situation all across the world? How are we actually taking the satellite data and ground truthing it so that we can make sure that it's accurate?
That's a huge challenge. That's the last mile of the marathon. It's about impact collection. It's about working with people on the ground. And that's what we do at the United Nations and World Bank and other. We have some applications on the ground to do the ground truthing, but we need a lot more. There's other example. FuseNet's another good example. People on the ground verifying these products, and then do you trust it or not? That's the short answer. I know we're running late. Thanks.
Yeah, no problem. Thank you, Mark. Just remember, we'll have a nice long session after this to continue the discussion. So our final speaker of the session will be Jordan Christian. And Jordan is a postdoctoral research associate in the School of Meteorology at the University of Oklahoma.
Hello, well, thank you for having me. So today I'm going to be sharing some recent results and research on flash droughts in the context of climate change. But before again, just want to acknowledge the very large co-author team that was as part of this research project, as this was a very large collaborative effort. Sure this works. Okay, great. And also just a couple notes before I go on as well. So this is actually research from a very large global study. So today I'm actually just going to be doing a kind of an excerpt, taking a specific focus over the US. And just as a quick note as well, this paper at the time and when I put this together, it had been conditionally accepted. It's now formally accepted in a journal. So hopefully this will be coming out in a couple of weeks. So just as a little bit of background information, particularly a little bit maybe from a global perspective first, global population is expected to increase significantly over the next several decades. And with this increase in population, there's also going to be a very large increase in the associated agricultural demand as well, particularly by the middle of this 21st century. In flash drought, it's so important because it's at this intersection of impacting food security and water resources. And, compared to conventional drought development, we're working with much shorter timescales and much more rapid impacts on food and water resources. So this kind of led to a couple of research questions that just will kind of highlight the outline for today's talk. So first of all, just going to take a look at, where are the general trends of what we may be expecting to see if we look ahead in terms of the US and a changing climate. And then also as well, kind of an impact-based perspective is, what does flash drought look like over agricultural land in a future climate as well? So those are the two key things I'll be taking a look at and discussing today. So a little bit of background here for what we did for the flash drought. So we use CESAR, standardized evaporative stress ratio, and soil moisture as well to identify flash drought. Just as a quick summary, you can get the evaporative stress through ratio of evapotranspiration and the evaporative demand. This provides a general overall moisture stress on the environment. And, when I say CESAR, we're just simply standardizing this ratio. And I always like to show this as well, just to show schematically what this looks like. So when we're looking at something like evaporative stress, when it's rapidly decreasing, this is generally, for the most part, indicating drier, warmer conditions. And when it's increasing, it's the opposite, wetter and cooler. So in terms of flash drought, we're looking for these rapid decreases in CESAR. So I wasn't much in a math mood this morning, so I'm not going to really go into all the complicated details, but I'll just provide a quick summary here of how we identified flash drought for this project and study. So we actually used kind of a framework from two different papers that we did within the last few years using the CESAR metric and in conjunction with soil moisture. And so just as a quick summary of how we did this, so we're basically looking for this rapid drop off in CESAR to identify the rapid intensification towards drought. And then we also brought along soil moisture as well, just to help with identifying drought. So just making sure at a minimum, we're seeing some sort of drought conditions reached, making sure it drops below the 20th percentile. And then lastly, just making sure that this drought develops, flash drought develops over a couple of weeks, and it's not just, a dry spell or a very short time of a dry down. So background on the quick data sets. So I don't want to talk too much on this because I like to talk about figures, but we use just global reanalysis data sets for the last few decades. Use 6 different CMIP6 models here to project into the future to see what flash drought looked like. That's technical details, not worth talking about. In terms of the actual model scenario, so we had 4 different scenarios, the historical, and then we have 3 future scenarios. We can have a low end here with the SSP 126, middle of the road with the 245, and then a high end 585 to give us different perspectives of how flash drought may be changing or over the next century. So it's important. I like to always show the historical flash drought from the model perspective, because if the models can't show flash drought, or even from a climatological perspective, it can't represent flash drought, then there's really no point of moving forward. So we wanted to first see how well the models did capture flash drought. And so this is just taking a quick average of what the models were producing in terms of a frequency or a climatological frequency of flash drought over the past 30 years. And for the most part, there have been several studies that have shown that for the most part, the central US is a hot spot for flash drought. And from the models themselves, they're showing this as well. They are showing, for the most part, this hotspot region over the central US. So that was at least a good positive sign going forward, that at least can capture that central US signal. In terms of how well the models do compared to, say, more like observational data sets like reanalysis, we just did a quick look at this. We just subtracted the difference just to see how, if there's any differences. And there's a slight overestimation in the Pacific Northwest, slight underestimation in the Central Plains, a little more so of underestimating flash drought from the models in the Southeast. But for the most part, in terms of the math part, there's the black dots or stipples on this graph showing statistically significant differences. There weren't any for the most part. So this gave some confidence moving forward, at least over the US portion, that that the models are able to capture flash drought spatially, but also wanting to take a look at this as well from a temporal perspective, because that's important too, making sure we capture the seasonal cycle. So once again, just looking over the last 30 years, that red line on there is, or sorry, the black line is from kind of the reanalysis, observational data sets. That's kind of how you can view it. And then the red line is the models. And they actually did very good. They captured the seasonal cycle. They show that there's a higher flash drought frequency in the summer, which once again, this has been shown through numerous papers, that for the most part in the central US that we do see this. So this gave us a lot of confidence moving forward, that at least we could take a look to see what these projections would look like looking for. So that's what I'll be showing you here now. So this is just basically a quick summary of how flash drought frequency will change between the historical window, 1980 to 2014, up into the end of this century. And so the figure I'm showing here is actually the middle of the road scenario. So all the scenarios scale. So, if you're showing the low end, it's going to show slightly lower flash drought frequency. If you show the high end, it's going to show more. So I just want to show kind of the middle of the road scenario to show what we're looking at. And for the most part, showing a general kind of a small flash drought increase in terms of frequency in the western half of the United States and also the western half of the Central Plains. And then for the most part in the eastern United States, there's not so much. It remains, or at least it's projected to remain about the same. But we can break this down into time series. So on this graph here, this is actually now looking back again at the central US, kind of that hotspot region of flash drought, have that, the black line with the historical period, and then the various scenarios, just to show what they look like. And for the most part, all the scenarios do show a smallish increase in flash drought risk over this region, over the US. The high end scenario, the 585, showed the largest increase, and the lowest end also showed the lowest increase. But for the most part, they're actually all about the same, with about a 5 to 10, 15% increase. So it is a modest increase, but definitely I'll talk a little more about what that means from an impact-based perspective as well. But just as a very, very simple just want to show a simple perspective of the drivers of flash drought. When I say drivers, I'm just talking about very, very simple metrics, looking at precipitation changes, evaporative demand changes to see how that may be impacting flash drought frequency. And we saw with that, the FT is the flash drought, P is precipitation, PET is evaporative demand, and RSZM is root zone soil moisture. And for the most part, between all the scenarios, got to be careful with precipitation, but it's shown for the most part not so much of a change in precipitation for the central US, maybe a small increase, but we do see relatively larger increases projected with evaporative demand, and that is probably playing at least some sort of role in increasing the risk for flash drought in the central US, and why we may be seeing some projections of some high risk of flash drought here. So now on to the agricultural side. So this was very interesting and something I want to spend a little more time on. So what we actually did was we actually broke this up by continent. I'm just going to be focusing on North America today. So we're kind of zooming out a little bit more just outside the US and across all of North America. So in terms of just the actual perspective of just cropland by itself, not discussing flash drought first, that dotted black line is just showing the general kind of land area of agricultural or cropland across North America, and it's been increasing for the past 150 years or so. In terms of flash droughts impacted, or the land area impacted by flash drought, it's been increasing a little bit over the historical period. But we just want to take a quick look here, showing that actually, for the most part, it's projected that agriculture here in North America is not really expected to increase so much. But some interesting things occur when you actually start to look at the percentage of cropland affected by flash drought, and that's what's showing here. So this is actually the percentage of cropland. This, you can think of it as like an average annual risk based off all the climate models of impact over cropland. And so for the most part in the historical window, we saw this being pretty flat. The risk really didn't change too much. But when we look ahead in the next 70 to 80 years or so, we actually do see that there is a increasing risk of flash drought over cropland across all scenarios, but particularly across the SSP 585. We almost see kind of like almost like a small tipping point where when it gets to extreme, you start to see this very, very large increase in flash drought occurring over cropland. So that's actually all I had here. So I'll just summarize here. So once again, we saw some flash drought increases in the western half of the United States, pretty modest, but in the 5 to 15% range for the most part. And that did include a little bit of the central plains as well, where we saw the flash drought hotspot. Modest increases in flash drought. So I should clarify too. So this is an excerpt from a global study, and actually, the U.S. is actually pretty modest compared to many other regions. There were some, especially Europe and areas in South America, there were some pretty large increases. But for the U.S., just a little bit, 1.2% increase for the highest emission scenario run, and then just a 9 and 11% increases for the lower end runs. And then in terms of the agricultural risk, this was pretty substantial, particularly from the higher end runs, higher emission scenarios, 1.45 time increase, and then also for the lower ends as well, also seeing some increases as well, even though they're a little more modest. But that is all I have. Thanks.
Thank you, Jordan. We do have plenty of time for Q&A for this speaker, and then we can move into more of a discussion after that. Anyone in the audience, or do we have any online? We have Pam.
Working. All right. I'm Pam Knox. I'm from Georgia. So I was very intrigued by the map that shows it doesn't really capture flash drought in the southeast part of the US very well. Maybe you could talk a little bit about why that is, and then also whether or not we can trust the predictions of future flash climate if we can't even get the current climate right.
Yeah, so as part of the Southeast is a very interesting region. We've noticed before talking about the future part, it's a little more challenging to almost get flash drought going in the Southeast just because higher humidity and things of that nature.
It's not hard.
But
it's not hard.
But going, looking into future projections, we did take a look at some different variables. We looked at, like I said, got to keep it with a grain of salt, but precipitation, PET, and for the most part, there just wasn't substantial changes from that perspective, and that's maybe why there just wasn't that much of a change or an increase. But a lot of the changes, like I said, were not so much in the US, they were actually more focused in other regions around the world.
All right, well, thank you.
A question about one of your earlier slides.
Yeah.
It looked like when you were looking at the historical runs, and if I understood the scale right, in the central US, 50% of the years had flash droughts. And that, again, from what we've heard later, I was questioning that, right? That seems like a normal occurrence as opposed to what we would expect.
Yeah, so I will clarify here. So that southern portion of the US it's a tricky one. In terms of, I believe the relative frequencies once you get in north of Oklahoma and the Midwest and Northern Plains, looking at that 20 to 35% range, that I think that makes a little more sense. But one thing to keep in mind too is when we do this analysis for flash drought, and actually Jason kind of mentioned this in his first presentation, we're actually not looking at necessarily the sustained propagation or persistence into drought. So this is really looking at that, the rapid intensification part. So one thing to keep in mind here is if you're looking at, let's take Texas, for example, looking at that 40%, 2 out of every 5 years is showing a flash drought. What that's meaning here in the context of how we identified it is saying we saw that rapid increase, and yeah, maybe it reached, for example, D1 drought for a week or two, but maybe it didn't sustain itself. So if we did add a criteria where, we were going to force it to sustain for, let's say, a couple months, this would significantly drop off. And yeah, we would be looking at much lower frequencies and percentages.
Thank you.
Yeah.
Okay, do we have other questions? Anything coming in online? We have
Actually, I just wanted to follow up. I often struggle with those figures too, because you think there can't be drought in 50% of the years. Important thing to keep in mind here is that we're actually looking at parts of those years. So you could actually have a drought that occurs for, a couple months in the spring of one year, and then the fall of the next year. Those could count as 2 flash droughts. Even though it's not the entire year, it's kind of misleading in a way, presenting it as 50% of years. It's actually 50% of parts of these years. So like if you take drought should happen 20% of all years, but it's like parts of those years again. You know what I'm trying to say, or?
Yeah, we're going to quickly jump into a philosophical question about what is flash drought based on this. Dan, can I ask a question?
Yeah, I think we'll take one more question related to this specific talk and then transition into our discussion.
Sure. Can you go on to one of the slides where you're showing, it was a bar chart where you're showing different frequencies for the different scenarios? Further along. Yeah, this one right here. So under flash drought, you have different frequencies here for SSP 126, 245, and 585. So what about those scenarios led to this? Because there must be something in there that's leading to a decrease in the percent change for the 245 compared to the 126 and 585.
So that actually probably is a statistical artifact, and I'll actually show you why. So if you actually look at this time series graph, the reason is because the window that was taken, the change, you can notice that the SSP 245, it started off a little higher, even though we were doing 30-year smoothers and things like that. With that specific year, just extracting that one value, it's higher. So when you take that change, it produces this where you get that change. So there could be a little bit of statistical helping there to help kind of smooth that out, probably a little bit more. But yeah, that's for the 126 and 245. That's why we're seeing those differences. Yeah.
Yeah, if your paper hadn't been accepted yet, I would say you probably need some error bars on there. You're saying there's a statistical artifact. It means your sampling isn't enough. So you have a lot of errors surrounding that.
Yeah, well, yeah, and we do have the error bars of the variability here, even though it's hard to see on that. But yeah, right, I agree.
Okay, thank you, Jordan.
We do have one virtual question if we have time.
Yep, let's take that question now.
Okay, based on the PowerPoint about the data, what are the main steps to process the data to identify flash drought?
Yeah, that's a great question. So yeah, I did not want to provide very boring slides on how to do that, but essentially that process was to extract ET and PET. You're having to derive PET from the CMIP6 models. You can get Caesar. And then there's a couple steps there where essentially we had to smooth that time series and then take the changes, kind of the change or the standardized change and things like that in order to get the metrics to quantify flash drought.
All right. Thank you, Jordan. All right, well, I want to thank all the speakers. That was a great way to kick off the workshop here. So we got about 40 minutes now before lunch where we want to have an open discussion. This should be two-way with the audience and the panel members, not necessarily just questions, but discussion back and forth. Kind of on this state of the science, what's remaining to the audience members, question-wise or topics moving forward. And I guess before we do that, are there any sort of presentation-specific questions that were missed that we didn't get to yet that you want to ask any of the panel members? Mark?
I did have that earlier question for Highland I wanted to ask, since it came up a couple times in presentations about machine learning. Your thoughts or Andy's on the prospects for how that's changed the game or will change the game, and your confidence in being able to better predict droughts?
Are you talking about the statistical prediction tool that machine learning can be potentially helpful to?
As general as you want to make it, machine learning in general.
Okay.
And understanding the relationships of what you all look at in modeling to better predict drought.
All right. The reason that we mentioned statistical prediction tool is really because we want to take into consideration and also incorporate all the possible tools to improve flash drought prediction. We know that prediction can be, really difficult to make. So with regard to, why do we want to consider statistical prediction tool? Just really because we need to consider other alternative tools, for example, dynamic forecast tools. The thing is to improve the skill based on dynamic forecast system, especially spending effort to really reduce model biases and improving model forecast initialization can be a daunting task, especially for some biases, which had been there for years or even decades, like WITCZ. It can take, quite some time to really to improve the model and reduce the bias. So the reason that I'm mentioning machine learning is that we just need to think about alternative ways or complementary ways to improve the prediction. If turn out, using statistical prediction tool, for example, data-driven, the machine learning methods, we can improve the skill. For example, find out the list of predictor and then predictance. If we can find some way to improve the skill, then we can combine the dynamic forecast tool and statistical tool together to improve the skill. This can be, helpful in certain aspects that dynamic forecast system are kind of challenging in simulating. For example, precipitation prediction. In dynamic forecast system, precipitation prediction is kind of subject to the model representation of the precipitation processes, which can be quite challenging because of the relative cost resolution of the dynamic model, and also people understanding of the specific precipitation processes, how they can be represented. But if we use statistical prediction tool, there could be some hope that we produce more skillful precipitation forecast using a list of predictor. So basically just just think about all the possible tools, and if one tool could be challenging, could take years or longer to improve, then need to think of alternative ways and combine them all together.
All right. Well, looks like we already have some thoughts from the audience here. I think if we want to come up to the microphone to state your comment or question.
We also have one virtual question for Highland too.
Yeah, so my question is also for Hainan. So Also, you have a flow chart showing that you need to run the land surface model offline and use the season to sub-season forecast variables. So may I know why do you need to run that land surface offline? Because I assume that the seasonal to sub-seasonal forecast model already has the land surface conditions there. So could you please explain more details on this? Thank you.
Yeah, this is a great question. We do know that the couple forecast system or the AGCM, some of the model only has this AGCM component. They do provide the forecast for land surface state, for example, soil moisture, evapotranspiration, and so on. But the reason that we instead of using these forecast directly made available in the original archive, we use this offline land surface model approach mainly because it has several added benefits to improve the skill, the forecast skill for the land surface variables. On one hand, using this offline land surface model approach can give us this flexibility of using more accurate land soil moisture initial condition, land initial condition, because for some of the existing forecast system, their initialization in terms of land is not that great. So if we can find some other way to really provide more accurate representation of the initial condition, we want to directly use that. And additionally, by using this offline approach, we can perform this post-processing, apply the post-processing bias correction and the calibration to the meteorological forecast to improve the skill and reliability of precipitation and temperature, which is, the key driver for flash drought onset and flash drought development. By using the land surface model of land, we can drive the land surface model with these post-processed meteorological forecasts to improve the skill of the land surface forecast. And additionally, there's always a time lag, between the land surface model used in the operational forecast system and the ongoing development of the land surface model. Just for example, for the ongoing the NOAA GAPS V12, the land surface model is NOAA, but EMC has been developing NOAA MP for several years already. So by using this offline land surface model approach, we can have this flexibility of using the latest and greater land surface model. For example, if it turns out that some new model can have this realistic representation of vegetation process, then we can use it to use the latest and greater land surface model to produce a vegetation prediction.
We'll go to Brian, and then we had a question online that we'll go to next after that.
All right. So this goes kind of to how Jason kind of kicked off the session, and he talked about, where we're seeing flash drought. We're seeing it being discussed mainly in agricultural situations, grazing and production. But then it kind of got into what Amanda was talking about and knowing what these impacts are. And I think I don't know if I'm really asking a question or more stating a comment, that I think more so than regular drought, with flash drought, antecedent conditions are going to play a bigger part of how we are identifying, properly handling, looking at the impacts. And it actually came out of why I bring this up is some of the work that Jason did in the 2017 situation with Tanya Hagan at the National Drought Mitigation Center. Was Tanya she's a social scientist and was working with the ranchers out there. And she came up to me and she said, a lot of these interviews we've been doing with these producers, they're talking about before it got dry, how cold it got. And what happened was you had this antecedent condition of a late spring freeze that impacted forage in this area, and then it got dry. Both occurrences by themselves would have been very problematic for these folks. You coupled them together and it exploded on the scene. And I remember I was a Drought Monitor author during that time. And I'm going through all the different data, and we're just not seeing it. And again, this is 2017, so not all the same tools, but we just weren't seeing it in the data, but the impacts were coming in. And again, it goes into, how are we properly
collecting the impacts and again, developing these baselines. But then these antecedent conditions that are leading up to these flash drought events. Like I said, in this instance, the flash drought probably would have been bad. And it did lead into a northern plains drought that was well recognized. But without the work that was being done by others to find out that, hey, there was bad conditions on the ground already that had nothing to do with precipitation, had nothing to do with dry soils and that. And it set the stage for something that got really bad. And I really think as our group, understanding these antecedent conditions more so in flash drought situations is going to be more meaningful than what we see when in a typical drought situation, right? So I don't know if anyone has a response to that, or like I said, I don't know if that was a question or a comment, but.
Just to chime in for a bit, yeah, I think what you touched on, Brian, was the importance of this locality, regionality, whatever you want to call it. Because if you talk to Laura Edwards in South Dakota, they actually had antecedent conditions going back to the prior fall that actually helped to condition the land surface, and then it got wet, and then it got dry again. So the antecedent conditions, you can go even further back to the variability, but then getting down to that local level where the impacts are felt.
I just wanted to say I really appreciate that point, and it makes me think about, in the kind of classic exposure plus sensitivity equals vulnerability. I think what you're talking about is a particular kind of sensitivity. Like we know about the exposure. You've got the flash drought numbers. You can see it in a lot of the indicators, particularly that some of the folks on the panel are thinking about. But it seems like we're saying that for flash drought, maybe the sensitivity matters, or it functions differently than in some of the other situations that we're used to. And thinking out loud in front of a room of 100+ people, which is never a good thing to be doing. But I think your comment's really interesting, and I really appreciate it, Brian.
Thanks, Amanda. I guess before we go to an online question or comment, did anyone on the panel want to further build on that, or shall we move on?
From a political standpoint and policy standpoint, let me say though, well, two things. One, the Drought Monitor got hammered a little bit, and we knew about this freeze, but what it led to, sort of on the positive side, is introduced legislation by Thune to bring about this huge network expansion in the upper Missouri Basin on the Mesonet side. And I think there's some long-term O&M questions I have about it, but in general, this is a positive that came out of a negative. We tend to think negative impacts only when actually this was some lemonade out of that flash drought.
Thanks, Mark. So let's go to a question or comment online. I don't know who's queuing those up.
Yeah, Dan, I think it was for Haylan, and I think it was actually answered by her last response. So we're good.
Okay. Are there any others online at the moment?
There is not.
Okay. We'll go over to Art.
Well, hopefully you're not quoted in saying, if you mess up every once in a while, good things come out of it. But I actually have a question for you, Mark, about your machine learning for flash drought. I mean, how inhibited are you by the just lack of flash droughts? It doesn't seem like you have a very big training sample in that.
Well, I thought you were going to ask me, what are we truthing it against? So there's a there's challenges
You
with that,
increase
right?
your sample size by your choice, right?
But yeah, so no, that's obviously right. That's some limitation, but flash droughts just didn't begin in the last 20 years. They've been there, right? But we didn't call them that. My motivation for using it originally in the media in 2000 and then our BAMS paper in 2002 about the Drought Monitor was to just raise awareness of drought, which was like the forgotten kid on the block that no one wanted to play with, but yet had per capita second largest economic impactor of all the hazards, and globally probably more so due to famine and other related issues that fortunately we tend to generally avoid, although we have issues here too. And I think COVID has illustrated supply chain issues that drought causes in fuse related countries. So I think that is part of the problem, Art. Yeah, I think a lot more to do there. And then what do we treat it against? And that's where, you know, hopefully that drives some potential future research and ideas from folks like you in the room that can help us get there.
Just a quick follow-up, if I may. You treat a flash drought in the Northeast the same as the Midwest, the same as anywhere in that case, right? They're all thrown in to the mix.
I mean, through these type of analyses and the changes, I think when you're looking at that, yes. I mean, based on the initial stuff, I think the other perception we want to totally, and it's great to see a lot of people east of the divide here, I might add, the drought isn't just a Western phenomenon. And maybe this is what we've got going in the Northeast this year as it brews. We're just waiting for the temperatures to kick in. It's been one of these sort of cool droughts. Same in Nebraska. I mean, the dust storm in Illinois, 40-mile-an-hour winds, you know, in Nebraska, same sort of situation as we wait for Mother Nature to turn up the thermostat a little bit, and then boom, it can happen fast, right? And that'll be the impact part of it. But yeah, I think the short answer, you guys, Jordan, or you guys could correct me if I'm wrong, that we're looking at that sort of in the same vein in terms of East versus West, or Midwest for that matter.
Thank you.
All right, we'll go over to Joe.
Thanks for all the great presentations today. I'm struck and excited by how many comments and speakers mentioned, I think, the value of impact-oriented information and trying to find a way to really link that to indicators and maybe even a forecast. I'll offer up one example and then ask a question. The example is and not a perfect analogy for drought, but what the Weather Service is doing with the heat risk tool, I think, is a great one to consider. So in the West, the Weather Service now has forecasts that not only are looking at low and high temperatures over a particular period of time, but are linking that to CDC modeled heat mortality based on past statistics. And that modeling can be not only locally specific, but also changes throughout the year. So we don't have a fixed threshold for where we consider a heat wave potentially dangerous. It can change. July in Phoenix is very different than May in Phoenix, and those are both very different than Seattle any time of year. So impact information has been fused into the forecast process. Granted, it's not a perfect analogy, short-term weather forecast, and we're dealing with just heat mortality. But I'm curious if the panelists think there are opportunities for specific variables that could be used for drought. So it could be, are people, fallowing fields? Are they selling cattle? Are they hammering groundwater? Like, I'm curious, what types of impact information might we want to start with if we went down some sort of road to, link these indicators or think about forecasts that are explicitly tied to impact information?
Maybe I'll take first stab at that. Part of the problem, I totally agree with you, first off, is the privacy nature, that they don't divulge down to the scale or resolution that would tie into our indicators. Preventive planning, typically traditionally thought of on the flood side, is now being applied to drought for over 10 years. But yet, even crop planning intentions of knowing what acreages are covered by which crops, until there's emergence and enough canopy to monitor it by satellite, you're flying blind a little bit. So there's still some challenges with some of that, I think, on the impact collection, that's not real time, but rather retrospectively when all the data comes in and they do their censuses and they do their natural resource inventories and things of that nature, doesn't marry up with the spatial and temporal resolution of our indicators. That's my short answer.
I can add to that, and I definitely agree with Mark. Two places I think there might be opportunities there. And again, I think there's a number of steps between saying it's interesting, there's an opportunity, and getting to where we actually have models that link it the way you're talking about the heat index with weather. One of them I think that's particularly interesting is around public health. I think that there's been some really interesting work coming out around linking conventional drought and public health. And the question of whether flash drought emerges more quickly, and we see that in the public health data, is a question I'd be really interested in, especially because I think for some of those public health impacts, we have, you know, maybe more robust monitoring, just because those are some things that are already being monitored for public health reasons. And then the second one, to maybe put Jason on the spot, the Coping with Drought project that you're involved with, thinking about ecological indicators, because I think, again, ecologists are very interested in kind of identifying those mechanisms for ecological reasons. That's something I know my agency has done a lot about. And your project's one I know in particular has been thinking about this. So maybe you want to talk about that, if I can throw it over to you.
I think what I'll actually do is I'll see if Jamie McAvoy is on this call. I know she was on the attendee list. Because they've been having interviews with people. And I unfortunately have not been able to join any of them because of extensive travel the last month. So I can't give any feedback on that.
Does not look like Jamie is on right now.
Okay.
Well, I can say a little bit more. I didn't want to talk about Jason's project himself, but I did chat a little bit with Jamie when I was putting the presentation together. And I think that, and you know, one of the slides went ahead and cited that preliminary data. They have not finished the analysis, but I do think that they are starting to think about what those indicators might be. And the fact that ecological drought is something where there's been a lot of work on indicators in particular. One of the ones Jamie called out was that high evaporative demand. And so some of the ecological processes or functions that are important, where we have models that are trying to link water or soil moisture or sort of fuel loading, like just what those different indicators are to what we already know about ecosystem health. So James, if you watch this, I'm sorry for butchering your data, but there is active work on that. And the hope is to actually be able to link it in some of the ways you're talking about.
Yeah, I think just to follow up on that, ecological drought is so different to work with than, so many flash drought studies have focused on ag impacts. And those happen quite quickly in the grand scheme of things. You might get a drought and you could see the reduced yields, just a month or two later. Even quicker if you're talking about, hay and alfalfa pastures, whatnot. Ecological impacts occur over different time scales. Like it's been really interesting to just learn more about like drought impacts on forest. The drought happened this year, but the impacts don't actually occur until next year or the year after that. It's a whole different paradigm to think about here. How do you address those kinds of impacts? How do you quantify them? How do you relate them back to the flash drought in question? It's a challenging problem.
All right. Well, I think we've captured a great theme there on linking flash drought to impact-based indicators at different sectors. Let's move. We got a little bit of a queue developing here, so let's move over to Joel on this side and see where we go.
Thanks. So this is a question that was spurred in my mind just right at the tail end of Jordan's talk, but the question really could be for any of you. So if drought requires impacts, and a flash drought, especially based on Jason's definition from your 2018 paper, is this period of rapid drying that leads to impacts. But Jordan's talk, you looked at periods of rapid drying that may not necessarily lead to impact. So my question is kind of about semantics. Should there be a better word to describe these weather events that could lead to a drought if the dry period were to continue? So we're looking at heat waves, periods of high evaporative demand, but we don't really know what's going to come after that. And there may not be a drought that follows. Should there be a better word for that?
A better word, which word? Drought or flash?
No.
Or what do you mean? I mean, maybe I'm not reading you right, Joel.
Sure. So from Jordan's research, he was looking at periods of rapid drying, but may not necessarily have led to an actual drought that continued. There may not have been impacts. We don't really know. So should we be using the term drought or even flash drought to describe this period of rapid drying if a drought doesn't actually follow?
I think, and I won't speak for Jordan on that, but the difference between Caesar and us saying flash drought is that with our flash drought definition, we expect impacts. We expect it to manifest into some form of drought and not just be a 5-10 day pentad decadal dry period that leads to no impacts. But those sort of tools help us determine if we're going down that road, and then we need to see if there's impacts. So for me, they are separate, but that's why I think in our definition that we go back even to our earlier definitions that predate this recent BAMs, we've always put impacts in our definition. And that's why I think we even put it in our original AMS statement too, many years ago. I think impacts was critical to differentiate it between all these other phenomena that might lead to a drought, so to speak.
Yeah, and that's one reason why, flash drought definitions usually require that indicator getting below the 20th percentile. Because then we can infer that impacts are happening, because that's, a widely used definition for drought. So as long as that rapid intensification leads to that indicator being below the 20th percentile, the implication is that drought impacts are occurring.
Yeah, I'll just chime in a moment here. The way you frame the problem will determine your results and conclusions. We have a common thread here about impacts, obviously, just based on what Dan highlighted. But when we're looking in climate models like Jordan looked at, or I oftentimes look at, you don't have little people running around in them and you don't have little cattle going in them, right? So what you need to do is you need to actually create an objective definition and to try to draw conclusions from that. So we don't have that kind of luxury to go back and look at impacts assessments in a lot of the data that we have, whether it's early data within our historical record or within climate model simulations that we use to test these hypotheses and draw conclusions. So again, how you frame the problem will determine what your outcomes are.
Yeah, that's a great point on challenges with looking at projected and modeled droughts versus what's actually happened on the ground. Okay, let's go back over to this side of the room.
Yeah, and Dan, I just want to jump in. I do have another virtual question when we're done with this one.
Okay, we'll come to online after that.
Okay.
Hi, thank you for the great presentations. My name is Kushan Mohammadi from University of Connecticut. I want to ask, I think my question is kind of same as the previous questions about the flash drought. We saw that, for example, flash drought, the drop of our condition from wet condition to the dry condition, or even for a dry condition to a drier condition in a rapid sense. However, I think in Southeast, what happened is that we had the very wet conditions, and then we had that rapid intensification, but it didn't get dry enough so we can have that impact on those vegetations there. But I also have these questions about in the dry regions. Because in those regions, we also have vegetations that they're not vulnerable to those rapid change of the soil moisture. So they kind of adapted themselves to those dry conditions. So are we also consider them as a dry? So there is a dry, we have a very rapid intensification part, and it gets very drier. So is it also considered as a flash drought? And I think you mentioned that if our drought starts as a flash drought but continues as a conventional drought, for example, for months, can be in our analysis for the duration of a flash drought, or for example, for those statistical analysis, can we say the whole durations a flash drought, or just that rapid onset development part as a flash drought? And one last question, not related to this. You also talk about the spatial resolutions of some of the data that we are using, Dr. Actin, that we are using in this in our tools. But how much is fine, how much is coarse? Because, for example, if we want to just look at those hot spots and regions that are vulnerable, for example, we can use a coarser resolution. So it's really depend on our applications, right? Thank you.
So I think we could start with that first question that I heard, which was, how do you look at flash drought in a semi-arid or arid place? I think that's what I got out of that first one.
Sure, I'll take a cut at this one. So I would argue that the flash drought research that's been done the last decade has been heavily biased towards wet areas, to agricultural areas. And as such, the definitions for flash drought have been constructed in such a way to actually detect flash droughts in those locations. But if you look at the framework for flash drought, people like Mark and I, we've always advocated for rapid intensification. That can be applied to any kind of drought. Right now, it's always been focused on ag drought, but I would make the argument that you can have hydrological flash drought too, for example, where if you're sitting in California and you go, wow, usually it takes 3 or 4 bad years to actually get the reservoirs this low, and this time it only happened in 2 years, I would argue that's a hydrological flash drought. That'll never be captured within any definitions that we currently have, because they haven't been designed to look at that. But it doesn't mean it can't happen. And if you think about like the desert Southwest, can they handle a bad monsoon? Yeah, it happens often down there. Can it happen a bad winter? Can they handle bad winter? Sure. Could they handle that back to back to back to back? Probably not. And how often does that happen? I don't know. But if it does happen, that might imply that this was an unusually rapid fall into drought that happened over a 2-year period. But by their measures, that's rapid. So it would take having to construct new definitions to really get at that problem.
And I think for the sake of time, we'll move on to other questions, unless panelists have more response to that first one. We'll move on. I think Adam had another one online.
Yeah, that's right. What types of open data do you think could be used to identify flash drought at a basin scale?
How big is the basin?
Not sure at the moment.
Yeah, right below the chat box is so-and-so is typing. So we're waiting for Adam.
Any other responses?
Well, I mean, in my opinion, it's going to depend on the spatial scale of your basin. If you're talking about a Huck 2, if you're talking about like the size of the Missouri basin, then that's probably not going to be the way to approach it, because we know how local these things can be and how things can vary so much. So it's really a concept of scale. Are you with the appropriate scale to be able to detect a flash drought that is representative of an area local to a given point?
And I think in some ways that gets to the previous question about spatial scale of the data and what really matters for flash drought. All right, let's move over.
Right. Can you hear me? I'm Carson with the Natural Hazard Center at CU Boulder. And my question is kind of a continuation of this impacts discussion we were having a few questions ago. But we didn't really talk about wildfire, which was brought up a couple times as a potential impact for increasing that risk. And given that climate change is also increasing the impacts of wildfire and smoke has a health impact, I'm just curious where we're at with thinking about how flash drought specifically is leading to increased wildfire and maybe just some conversation about those kinds of impacts.
So I don't think people have looked at it too closely yet. I mean, I would think about it more as, trees are going to be drying over long time scales, but the understory might be drying out more quickly. And, that's been one of the big causes of the really intense forest fires. I know climate change gets a lot of the blame, but a lot of it's been forest management too. Where there's been this buildup of, material to burn at the surface. And, it's like you take like California, for example, with the incredibly wet winter, this next year, they're going to be growing so much stuff that's going to be burning next year. And California works on a different time scale again, but like if you move to the Southeast, if they had a wet summer, lots of growth within the forest, and then it quickly dries in the fall, and all of that material becomes, dry and desiccated, that's going to lead to an increased risk for fires, due to flash drought. I don't know if that really answered your question, but.
Well, I just was wondering if people are like starting to think about how to quantify that impact, I guess, or like really dig into these cascading impacts related to other hazards. Yeah.
I mean, that's something that we might get into with our Montana flash drought ecological flash drought study, but we just started that last fall, so we don't really have too much to say about that yet, but that's going to fall out of that project, I would bet.
And I would extend it to not just the forested regions, but the grass fires. We're seeing that. And again, antecedent conditions play a role. So what's the lag between wet conditions enough to build up fuel to dry out to cause more intense fires? And I know NIDA specifically did some fire, maybe a report, right? I don't want to speak for them, but so people are thinking about it. And, just on the impact side, going back to your first original comment, the one thing I wanted to interject there that I think Amanda said so well is the rapid onset part of it isn't necessarily what's unique in those impacts. It's just that they come on quicker, that might still be the same as traditional impacts, but the onset is quicker. So, and then the last comment on the impact side, I want to mention that, we've tried several times through proposals to get funded is to work with National Phenology Network and others on the ecological side. It just doesn't go anywhere. Well, until it's important to their programs, somehow changing the mindset of those, making those calls on the research dollars, it's an uphill battle. But to me, that's a fertile ground right there. NPN, Nature Notebook, what are the rangers seeing in the forested areas and the national parks? We've got folks out in some of these areas in ecological, natural areas. We don't have to just make this an agricultural thing.
I would agree with all of that. I have not seen anything that is framing this problem from the flash drought side, but I do think there's things that we know from the drought and wildfire side that potentially speak to it, and that, someone could start trying to make that link a little bit more from the flash drought side. I think from the wildfire community side, there's a lot that, the agencies and wildfire practitioners know about fuel moisture and how that evolves over from the start of a season to the end of a season, and how it plays out in different ecosystems, different fuel types. And so those specifics, I think it goes back to that question that was asked about, okay, how do we link those dynamics to the specific impacts and the specific flash drought conditions? So that's not quite as specific, but I think that it may also be a matter of trying to link some of what's been done in the fuel moisture and fire science community with what's been done in this kind of indicators and flash drought community.
If
I
I
did
could
want
just
to
say
mention really
Oh,
quick, sorry, we had a comment from online. Richard, are you unmuted here?
Yeah, I'm unmuted. Can you hear me okay?
Yep.
Yep, all right. Yeah, I'm Richard Carr, Natural Resources Canada, Canadian Forest Service. Just my ears perked up a little bit when there's talk about forest fires, and been hoping to, one of the things to get out of the flash drought workshops is just better understanding of how to define them. And I've had a feeling in the back of my mind that some of the recent years, 2017 and 18 in particular in British Columbia, were probably related to a flash drought, with fairly good precipitation through the winter and spring that just suddenly shut off. And, from mid-May onwards into summer, the rain just basically stopped. So probably had a fairly rapid onset of drought in those regions. I mean, it's southern interior BC is, semi-arid to begin with, so there's not a huge amount of rain, but, I think coupled with that, a lot of the forest fires that we got, of course, are, you have to have a cause for them. And a lot of that was lightning, and with the lightning, not very much precipitation. So, we're certainly interested in flash drought development in relation to forest fires. We certainly see things like that maybe in the West. Haven't really looked at that type of event in the rest of Canada, but the western half is generally dry. The eastern half is quite a bit moister, so might be maybe different. I guess different things to look at. We've had maybe some episodes in the Atlantic provinces too, where it's normally fairly wet, but they do have a spring fire season, and last year it kind of took us by surprise with a big fire in southern Nova Scotia in April. And the provinces are much smaller there, so it's kind of easy to maybe overlook specific regions there. So, but I'm certainly interested in all of this conversation, maybe how we can apply it to forest fires, and especially since that's what I'm involved in. And just a few other aspects of forests. I deal with forest fires, but we've got insect and disease people, and maybe the flash drought has got some other types of insect or impacts on insect outbreaks, tree mortality, things like that. So yeah, I'm certainly interested in seeing where all of these conversations go. Thank you.
Thank you for that. And I think with that, we're going to have to cut it off here. There's still a lot of questions to be asked, but this was a great discussion. I think wildfire and flash drought is another kind of key theme we've hit on that needs more attention.